Okay, let me just upload our lecture here. And we are going to do a little math review today. And the first thing I want to do is just review with you the base units in physics. In distance, we're going to be measuring things in meters. Mass will be measured in kilograms. And our other base unit is for time, which is in seconds. So these are our base units, and every other unit in physics is a derived unit. For example, force is mass times acceleration, or kilogram meters per second, which we call a Newton. Acceleration is velocity divided by time, or meters per second squared. And velocity is distance over time, meters per second. Those are what we refer to as derived units. The symbols for distance are either x or y. Velocity is v, acceleration is a, force is F, and mass is M. So you want to make sure that you refresh yourself with those so that when you're reading problems, you'll know what kind of information is being given to you by the units. When we talk about dimensional analysis in physics, what I'm really referring to, and of course, you guys should know how to make conversions, but really you'll probably be using some tool to do that for you, and that's fine. But you do need to be able to show how units cancel out in a problem. So, for example, if you're using this problem and you're solving for acceleration, right, then acceleration would be equal to Vf minus Vi all over t. When you plug in for Vf, you're going to be plugging in meters per second. And when you plug in for Vi, you're going to be plugging in meters per second. And when you plug in for time, it's going to be seconds. And that's going to give you meters per second all over a second, which is indeed meters per second squared. So we want to be able to show our units and show how our units either cancel out or multiply to create the new units that we have. Also, when you're showing work and finding solutions on worksheets and in labs and in on your exam, you're going to want to round everything to 3 significant figures. So how do we count significant figures? Well, first of all, if a number has all non-zero numbers, then every single number is significant. So 1, 2, 3, 4. There's 4 significant figures here. If there's a 0 in between any of those numbers, it is significant. If there's a 0 at the end to the right of the decimal, those are significant. But what about this number? So 002 only has one significant figure, because when I put this in scientific notation, it turns into those zeros are just placeholders. So there's only one sig fig here. So remember, if I need to round this to 3 sig figs for an answer on my test or whatever, I'm going to have to add 2 zeros to the end to give it 3 sig figs. Just want to be careful with things like that. All right, so let's just review what a vector is. A vector is illustrated with a arrow pointing in its direction, and the length of it is its magnitude. Displacement, velocity, acceleration, force, momentum are all the vectors that we talked about in Physics 151. So if I put this on an XY axis here, let's talk about this direction. So we could call this could be a compass direction, right? Where I need to describe this angle relative to the axis it's touching. And it's touching the east axis, and it is north of east. Or I can use polar coordinates, which are measured with angles measured from the positive x-axis. So in the case of this one, if it's 60 degrees, the polar heading is 60 degrees. But what if it's 60 degrees south of west? So if it's 60 degrees south of west, like this, 60 degrees south of west, then the polar heading would be this all the way over here. So because it's in the third quadrant, whatever the angle is, I have to add it to 180 to get that total big angle. Second quadrant, I have to subtract it off. Third quadrant, I take it off of 360 to get the angle relative to the positive x-axis. Let's just do a couple examples. So if you had 100 newtons at 180 degrees, okay, that would be the same thing as, so here's our little pointing here. So it would be 100 newtons west. What if I had 100 newtons at 120 degrees? Well, if I did that, I would go 90 and 30 units over, right? So that would be, that angle would be the same thing as 30 degrees. And let's look at that. That angle is 30 degrees to the west of north. Vectors also have x and y components. So when I draw a vector, and let's say that I'm doing this one here at 120 degrees, it has an x component and it has a y component. The x component is going to be a negative number, and the y component is going to be a positive number. It's just like a point in space, really. So if I want to know what it is, so let's say this was 100 meters per second at 120 degrees. X is always going to be equal to that value times cosine of the angle, and y is always going to be equal to the hypotenuse times sine of the angle. So in this case, it's going to be 100 cosine of 120, which is going to give us negative 50 meters per second. And this one's going to be 100 sine of 120, which is going to give us positive 87 meters per second. All right, so if I give you the x and the y, you should be able to figure out the hypotenuse, the magnitude, and the direction, the r and the theta. So how does that work? Well, let's just draw in. The x is negative 100 newtons and the y is positive 100 newtons. So our resultant is this right here. We're going to want to find this angle with tan theta, and we're going to want to find r with the Pythagorean theorem. So r squared is going to be equal to x squared plus y squared, which is going to be equal to 100 squared plus 100 squared, or 2, 1, 2, 3, 4 square root Newton squared. And when I do that, I get 141. So R is going to be 141 newtons. And the way we find tan theta is we find y over x. Well, y is 100 and x is negative 100. We take the inverse of negative 1, and that is going to give us, so when I take tan negative 1 of negative 1, I'm going to get 45 degrees. It's going to be a negative, but I'm going to ignore that because what that's telling me is I have to do something with that number. So remember, my polar heading would be this one. I'm the second quadrant, so I'm going to take it off of 180. 180 minus 45 is 115. That's not right. 135 degrees. Or I could just say 45 degrees, which is southwest. Not south of west, but southwest, directly in between them. And another thing I want to review with you is unit vector notation. So unit vector notation is a more mathematical way of writing the x and y components. And what we do is we define something called a unit vector, which is a vector that has the magnitude of 1 and it points in a certain direction. So unit vector I points in the x direction and unit vector j points in the y direction. And when we find our x and y components, so imagine we had 100 meters per second at 30 degrees. The x component is going to be 87 meters per second, and the y component is going to be 50 meters per second. I could rewrite this as a mathematical statement. That velocity is the vector sum of 87 in the I direction plus 50 in the j direction. And then I can put my meters per second on the outside, so it's not as confusing. That's just a little neater way of writing the vectors out, and it's really easy because this number in front of I is always your x component and this one is always your y component. So if I give you an example of a force that is 10 newtons in the I direction and 20 newtons in the j direction, Fx is 10 newtons and Fy is 20 newtons. I can find the magnitude by taking 10 squared plus 20 squared, taking the square root. I can find the direction of that, and it's in the first quadrant because both of these are positive, so my direction will be a positive number. And finally, we need to be able to add vectors, especially vectors that are not at at right angles to each other. So let's just change this one to be 180 degrees and 30 degrees. So let's just sketch this out. We've got 100 here going west, and then we have another one here going east. So if I were to add those, right, my resultant is going to be this vector here. So it turns out that the resultant's x is the sum of these two x's, and the resultant's y is the sum of the y. So we can make a little chart where we take the I and the j. So 100 newtons at 180 degrees, well, that's going to be negative 100 newtons and 0j because it's on the x-axis. Call that vector A. We're going to call vector B. 100 times cosine of 30 is going to give us 87 newtons, and 100 times sine of 30 is going to give us 50 newtons. So for my resultant, the I component is going to be negative 13 newtons, and the j is going to be positive 50 newtons. So if I want to find the magnitude of that, I'm going to take negative 13 and square it, and take 50 and square it, and then take the square root. And you should get 51.7. So the resultant's 51.7 newtons. And now to find the angle, and notice that it's got a negative x and it's got a positive y, so it's in the second quadrant here. So we're going to have to subtract whatever our angle is off of 180. So tan theta equals 50 all over negative 13. And then I'm going to take the inverse tan of that. So 50 divided by 13. I just dropped the negative because I know I'm going to have to adjust for it for second quadrant. And then I'm going to take the second tan, and I'm getting 75.4 degrees. If I want to describe that, that's west of north. Actually, it's not. I'm sorry. It's north of west. It's this angle right here, where y over the adjacent. Or it's 180 minus 75.4, which would be 104.6 degrees. So 51.7 newtons at a heading of 104.6 degrees.